Hi, everybody, and welcome to today's edition of the Spectral Geometry in the Clouds seminar. Today we are having Grigori Rozenblum, who will talk to us about Weyl asymptotics for the Poincare-Steklov eigenvalues in a domain with Lipschitz boundary. As usual, if you have questions, please unmute yourself or ask them in chat. Grigori, the floor is yours.
Okay, thank you very much. This is a little bit unusual talk because in many talks at this seminar there are many theorems and many results, many explanations. In this talk there will be one theorem which is more or less known. So it was supposed to be correct for many years, but now I'm happy I was able to prove it. And what I'm going to say is explain the main steps in proving this long-standing theorem. So it's Poincare-Steklov eigenvalues. So it is the Steklov problem, which is a very often topic at this seminar. So it is written here. So the standard Poincare-Steklov eigenvalue problem. It is the problem Laplacian in the domain with the spectral parameter in the boundary condition. One a little bit unusual thing that the spectral parameter is put here to the power -1. The reason is that we are going to use compact operators there, so it's more convenient to have the description of Steklov eigenvalues as eigenvalues of some compact operator. So the notation here is we have the domain, sigma is the boundary, and it is Lipschitz. We keep it with the surface measure induced by the Lebesgue measure in D+1 measurable state dimension space. So the measure of the dimension of the boundary is D. So it's a very old problem, and with huge number of applications, and I just checked that MathSciNet shows more than 600 publications where various aspects, facets of Steklov type spectral problems are dealt with. So this problem is closely related to the so-called Dirichlet to Neumann operator. So this is the explanation of what is this. It maps Dirichlet data to Neumann data, and among many other topics about this operator is the eigenvalue asymptotics, which is expected to be Weyl law. So when n of mu is the number of eigenvalues less than mu, if we write mu here, then this asymptotics is the area of the boundary times mu to the power dimension, and then some coefficient which depends only on the dimension. So this is the standard Weyl law. The first paper where it was studied, this Weyl law, where it is proved that it was quite long ago in 1955 by Lennart Sandgren in Sweden, and there were many generalizations and so on, and at some moment it was just a little bit tiny step left to have Lipschitz boundary. Lipschitz was a little bit better. It was a little bit better, but still this a little bit by some reasons was not possible to concur. So in order to understand the problem better, one needs to generalize it because it seems to be very hard to solve it as it is stated. So the more general, in fact, it was in the original paper by Sandgren that instead of the Laplacian operator, we consider some second order elliptic operator with, so it's elliptic, and instead of the Neumann boundary condition, it stands the so-called co-normal. So here it's related with these coefficients. Nu chi are components of the unit normal to the boundary, and Sandgren has a boundary of class C2 and coefficients of the class C1, and the weight function, which is a rather important object here, and in what follows, the weight function rho was continuous. The eigenvalues written in this form, you see here lambda to the power minus 1, they tend to 0, and Sandgren found the formula, which was later generalized a little bit. You do not need to look at the formula. The formula is, so it explains the coefficient, so the coefficients in the eigenvalue asymptotics. You see here it is lambda to the power minus d, because now we consider the eigenvalues of a compact operators. This is lambda to the power minus 1 y is standing. They are expressed in the terms of integrating some density alpha plus or minus along the boundary, and this alpha is expressed via beta, and beta is in fact the symbol of the Dirichlet-Neumann operator, and rho is the density here, and here since plus minus, it's also important because we do not require that rho is of constant sign. So it is all related with generalized Dirichlet-Neumann operator, and this is the expression for the coefficient in the spectral asymptotics, and one must see that this coefficient, the coefficient itself, it doesn't require any smoothness of these coefficients or the boundary. The measure on the boundary should be defined, and it is very convenient to consider Lipschitz boundaries. And since why Lipschitz boundary? Because the normal components, the normal to the Lipschitz boundary exists almost everywhere. It's the theorem by Rademacher some 120 years ago, and the boundary exists, the normal to the boundary exists, and this formula makes sense. And the question is how to prove it under the conditions, the very weak conditions that will be formulated very, very soon. So the weak conditions that they will imply that sigma will Lipschitz, and the coefficients alpha, beta, alpha will be bounded. The operator will be uniformly elliptic, and there will be a very, very, very weak continuity conditions which will be seen later. So here there are some words which saying that Lipschitz boundary for the theory of boundary value problems was of interest quite a lot in different topics, and it was often a hard problem to carry over the results of the boundary value problems to from smooth boundaries, from piecewise smooth boundaries to Lipschitz one, because a lot of mathematics breaks down, a lot of mathematical properties of a lot of instruments in the theory of boundary value problems break down when we pass from, for example, C1 boundaries to Lipschitz ones. It's a long, complicated story, and in particular the Weyl problem for for this Dirichlet-Neumann or Poincare-Steklov operator, this tiny step from C1 to Lipschitz, it was formulated as a challenging problem by Agranovich some 25 years ago, and it took so much time. A breakthrough in this problem appeared some 2 years ago when there was a paper by Karpukhin, Lagasse, and Polterovich, where they have proved the result. So they proved the asymptotics, the value asymptotics for the Lipschitz boundary for very special case when we have the Laplace operator, not an arbitrary second order elliptic operator, but the Laplace operator, and the most important thing that the dimension equals 2. Here the machinery, the hard machinery of complex analysis was involved, and it was not visible, for example, how to extend this complex analysis results to higher dimensions or to variable coefficients. But nevertheless, as for me, I was very impressed by this result by these three colleagues, and I thought that now it's time to try again to handle this problem. In fact, I, together with some friends, was attacking this problem about Lipschitz boundaries for more than 15 years, mostly without success. Well, so the main idea of proving the result for Lipschitz boundaries is the following. It is the idea of approximation of compact operators by better compact operators. So here one can see the main approach. So we have a bad operator K, about which we want to know its eigenvalue asymptotics. We want to approximate this operator K by some nice operators K epsilon, so that these operators K epsilon converge to K so strong that it's possible to pass to the limit in the formulas of interest. It works quite a lot. In particular, it was the approach, more or less the approach by Hermann Weyl in 1911, when he proved this famous result about Weyl asymptotics for the Laplace operator. Also, he used this kind of approximation, and it was used further on by many people. Especially, it was the large progress in this approach, perturbational approach, by Birman and Salamiak some 50 years ago. So I will refer, in this my talk, I will refer very much to some very old results. You see, I'm not young anymore, unfortunately, but nevertheless, I remember quite a lot of old mathematics, and I used a lot of old mathematics. By the way, it is not this talk, but as it concerns mathematics, it is a very important day today. So it's the birthday of Gerd Grub, who contributed a lot to spectral theory. She is 85 today and in very good form, and she is very active. So I want to wish her many more years of health and activity. Well, so this is the main idea. Now, concretization. The first thing that we need to find some compact operator describing the spectrum of the problem. Just here it is written that the convergence is so strong. So what does it mean, very strong convergence, in this particular topic about finding eigenvalue asymptotics? It is the following. So for some notations, so if we have a compact self-adjoint operator, then n plus minus, it is the counting functions of the eigenvalues, positive, negative eigenvalues, and there are these boldface quantities, n plus minus. It is lim. It's not lim. It must be, yes, it's lim. It's the asymptotic coefficients, if they exist in the asymptotic formulas of this kind. And for operators which are not necessarily self-adjoint, we have distribution functions of singular numbers. I remind you that singular numbers are the eigenvalues of k star k 1/2, and this n sup are lim sup of this quantity n at lambda k, where n, it is the distribution function of singular numbers, S numbers. So the strong convergence is governed by this Birman-Salamiak lemma, see, 1970. So this is the formulation of lemma. So let K be a self-adjoint compact operators, and suppose there exist apparatus K epsilon, for which we know the spectral asymptotics of order theta, and the n sup of the difference again with the same order theta goes to 0 and epsilon goes to 0. Then the result is that the coefficients have limits, and there are exist the eigenvalue these limits n plus minus their limits in the eigenvalue formulas, they exist also and are equal to this limit. So this beautiful lemma, which was the basic instrument in quite a lot of studies after that, it says the following: we must, here it's the strategy, we must represent the Spectr problem for a Lipschitz boundary as a compact self-adjoint operator. Then we need to construct approximating operator with known eigenvalue asymptotics so that the operators are compatible. It means the operators K epsilon and K act in the same space. And finally, to establish the above very strong convergence. So if these three steps are performed, then the Bierman-Sloniak lemma, it takes care of this passage to the limit. The natural idea, in fact, the technical idea which lies in the base of my calculation is the idea of approximated Lipschitz surface by smooth surfaces and tracing how the corresponding Neumann-to-Dirichlet operators converge. Do this converge sufficiently strongly? Here, I must say a few words about Lipschitz surfaces. More or less, Lipschitz surfaces are those for which which locally, it is written here, which locally are represented by a graph of a Lipschitz function. Lipschitz functions are those functions which have bounded derivatives. And Lipschitz bounded derivative, general functions in L infinity cannot be approximated by smooth functions in L infinity norm. But we are able to approximate them in some LP related norm. And it is possible that this a weaker approximation, which is possible, it take care of this strong convergence of operators. Now the setting, here I will say exactly what is expected. So we have a domain, bounded domain, sigma is Lipschitz boundary, and we have the operator. This is the operator, it's uniformly elliptic. The coefficient matrix, this script A, it is bounded, measurable, and it is continuous at the points of the boundary. So we do not require that the coefficients are continuous somewhere inside. They are continuous only at the points of the boundary. So they are L infinity functions which are continuous on a very, very small set. One might have asked for a little bit better coefficients, but in the course of approximations, transformations, we lose continuity. So only this very weak continuity. So now we have the weight function, which real belongs to LD, this is the dimension, and if d equals 1, it belongs to some d equals 1. So this means that we deal with a two-dimensional domain. It belongs to the Orlich space. Let us forget about Orlich space. And I will explain everything only in the case, for the case when dimension is 3 or greater. So d equals 2. So the theorem says that under these conditions, for the eigenvalues of the Poincare-Steklov problem, the asymptotic formula holds. The asymptotic formula, the same as was in Sandgren and so on, the same expression, but under much weaker conditions. This A plus minus one doesn't need to remember the formula for them. There are some coefficients which are expressed in some algebraic way. The integrand, the integral of some expression in the algebraic way of the coefficients of the values of the coefficients at the boundary and of the weight function. Well, so remember that the first step which we need to perform is to express the eigenvalues of the problem as eigenvalues of some compact self-adjoint operator. You know that we want to make some calculations. So it's called variational setting. So we define an operator by means of its quadratic form. So L is the operator. So L is our elliptic operator. So the economical derivative, and we need to consider not Dirichlet to Neumann, but Neumann-to-Dirichlet operator. How do you like that symbol? I invented it. And the Neumann-to-Dirichlet operator, so it associates with the boundary value of the derivative, the value of the same function, which is the solution. Since the solution of Neumann problem is not unique, we add some positive function v, which doesn't influence the eigenvalue asymptotics. This operator is self-adjoint, and our problem has the following expression: rho, this ND operator, and x was lambda f. The passage to variational setting is standard. It was used from even in Sandberg and many other people. So we take the quadratic form, this bold-face u, this is the expression, bold-face u, and take another quadratic form. This is integral of rho. Gamma is, what is gamma? It's an important object which will appear all the time. It's the operator of restriction of the function in the domain to its boundary. So we consider the space H1, Sobolev space H1, the space of such functions which are solutions, weak solutions of these equations. LU equals 0. The norm in this HL is defined by A of U, and in this space we consider this form U of U. It defines an operator, and it is this compact operator whose spectrum is the spectrum of the Neumann-to-Dirichlet of the Poincare-Steklov problem. So we have the one Hilbert space, we have the quadratic form, it defines some operators in the Hilbert space, and we are studying the spectrum of this operator. It's not convenient to work with quadratic form. So we define this operator H of rho, and we define this operator H of rho, and the first result is that for this operator H of rho, so the Neumann-to-Dirichlet operator, we have estimates of this n sub in the terms of d of LP LD. In the same case, norm of this weight function rho. Taking it together with Bierman-Slamiak lemma, it makes it possible to change this rho, that if we have some rho for which we know the spectral asymptotics, and it has convergence in this norm, then for the limit function rho we also have the spectral asymptotics. So this is the first case where we apply this Bierman-Slamiak lemma, and here this estimate, so it's the estimate for the eigenvalues of this operator, which we still do not know, and it is this coefficient, the n sub in this spectral distribution is estimated via the function rho. So a little bit of work is done. We have freedom in choosing the function rho.
Grisha, I'm very sorry. Can we go back to the previous slide for a second? I just missed the definition of rho.
Rho. It is some weight function which is real. It is a real function on the boundary. real measurable function, and then it's found that if these measurable functions belong to this LD space, then the operator is compact, and we have this asymptotics for these estimates for the eigenvalues of this operator H of rho. So
Thank you.
again, H of rho, it is some compact operator. We do not have formula at the moment, this, whose eigenvalues are our Poincare-Steklov eigenvalues. Next step, which is also standard, that is sufficient to prove for non-negative rho. That is a standard technique starting from Sandgren. So now we want to find some approximation. So we found the operator, we want to find some approximation following the general theory. So our aim is to find a change of variables in our domain, which transforms our domain with Lipschitz boundary to a domain with smooth boundary. But it is not just a change of variables. In the paper by Karpukhin, Lagasse, and Polterovich, it was the conformal mapping. We do not have this conformal mapping, and in fact, it has different nature. So we want to change it here. It's some geometry. So I remind you, there is a Rademacher theorem. The Lipschitz function has derivatives almost everywhere, and there is a corollary that Lipschitz surface has tangent plane, a normal vector. Again, new almost everywhere with respect to the surface measure. Another fact which we use, it was proved by Calderon that long ago, that if we have a compact Lipschitz surface, then there exists a smooth vector field, such that on the surface is normed by 1. It is uniformly transversal to the surface. And from this one can derive the following, that if the surface and the vector field are as above, then there exists a smooth surface, sigma bold, such that it lies in a small neighborhood and uniformly transversal to gamma. So this is a picture, a very rough picture. So this is our Lipschitz surface. This red are integral curves of the vector field, and this bold face is this smooth surface, which lies close to sigma and which is transversal to the vector field. So it's smooth. This smooth surface will be used to construct the change of variables. So we introduce variables x prime and xd plus 1 near, so in this part, so x prime will be the point on this smooth surface, and x prime and xd plus 1 is here denoted by t of d. It is the coordinate along the integral curve of the vector field. So it's the typical, so the point x has coordinate x prime and has coordinate this distance. Passage from the initial coordinates to this one is smooth. In these new coordinates, the surface sigma is defined globally now as a graph of some Lipschitz function. So in these new coordinates, the Lipschitz surface sigma is defined in these coordinates. Now the main invention is the following. I will write the change of coordinates. The change coordinates is the following. We introduce new coordinates, y and y prime yd plus 1. So the change is phi, where y prime is x prime, and yd plus 1, the transversal coordinate, is xd plus 1 divided by psi of x prime. So what is this? That phi transforms the surface sigma to a smooth surface. In new coordinates is y prime and 1 is a smooth surface. And the sense of this transformation is the following. We make stretching along the integral curves of the field of gamma. Well, this happens near sigma, and away from sigma, phi is glued together with the identity mapping. So you see, we make stretching, we make a bad change of coordinates because it's not smooth. You see, the function psi is not smooth, and the coordinates, so this change of coordinates is not smooth. Only thing we know that psi has bounded derivatives, nothing more. The inverse, in the inverse mapping, is the inverse stretching. One can write the formula. Properties of this phi, of this change of coordinates. So it is continuous mapping because Lipschitz functions are continuous. Derivatives in x prime variable are only bounded. First order derivatives, we do not talk about higher order derivative. But as it concerns xd plus 1 variable, then the components of our mapping and its derivative are infinitely differentiable in this variable. You see, this is the formula. This expression one can differentiate in xd plus 1 as many times as one wishes. Similar for the inverse mapping. The same is for Jacobian matrix of these mappings. So it is the Jacobian matrix is bounded in coordinates y prime and infinitely differentiable in the continuous and infinite differential in this only variable. Important thing here that this mapping, although it is rather crazy, it is an isomorphism of the Sobolev spaces, which is very convenient. It's not a simple fact, but I have found a reference. Now we apply the chain rule. What we are going to do? We want to see what happens with the quadratic form. The quadratic form will appear in a moment. What happens with the quadratic form A when we make this change of variables? You see, the quadratic form involves derivatives in the old variables. Now, by the chain rule, these derivatives will have coefficients which are derivatives of the change of variables, so they are multiplied by something bounded, and dx, the volume form, will be multiplied by the Jacobian, so multiplied by combination of derivatives. Well, we just said what are their properties. As the result, the quadratic form, which is written there, the quadratic form A, is transformed to the quadratic form in a new domain, in a smooth domain, with smooth boundary, but with discontinuous coefficient matrix. But it was discontinuous at the very beginning. Yeah, but it will be discontinuous even at the boundary. We suppose that initial coefficients are continuous at the boundary. Now they are not continuous at the boundary because multiplied by something bounded but not continuous. But the only continuity, the only regularity which remains is that these functions, the coefficients, are continuous in this yd plus 1 variable as functions with values in L infinity of sigma. The only thing, continuous, but at one point when yd plus 1 equals 1. Now we forget to save notation, we forget about the initial problem, return to initial notations. The functions rho and v are supposed to be smooth, and next thing is that we want to see what happens with the operator. Now in new coordinates we are able to write this operator H, which describes the spectrum of Poincare-Steklov in the terms of the Neumann operator in this domain omega, new domain. Namely, we take the quadratic form with domain H1, Sobolev space. It is a non-positive operator. We do not know how it acts, the operator. It's defined by the quadratic form with bad coefficients. But T1/2, the square root by the general theory, is an isomorphism of the Sobolev space and L2. It's so after a series of transformations, which we which are written explicitly, we have the following expression for this operator h. So it is, you see, t to the power minus 1, so it's inverse to the Neumann operator, so it's a second order differential operator. Then we must take gamma. Gamma is this restriction times by the weight function. Take this gamma. To this operator, take the adjoint. It is a bound operator. And then to the result, again, apply this gamma. This operator h acts on the boundary. Acts on the boundary. So you see, t acts in t minus 1 acts in L2 in the domain. Gamma restricts to the boundary. The adjoint operator acts to the boundary inside domain, and gamma returns it to the boundary. So we have some operator. We do not know how it acts, but we have a convenient description. It acts in the boundary. The next thing, next strategy, as described, is to find an approximation to this h. It is a bad operator. We do not know how it acts. T is a solution of Neumann problem with bad coefficients. So we make the following. We approximate the coefficient matrix A by a smooth coefficient matrix A epsilon in some rather strange sense. You see, the matrix A is bounded. We cannot approximate it in L infinity metric by smooth ones. We approximate it by by smooth in some weaker sense. So it's written here what happening. So we approximate A by A tilde, consider the operator H tilde corresponding to this tilde, and we will we will estimate the spectrum of this difference. Now the operators act in one and the same set, the boundary of this nice domain. And Birman-Slamiak lemma, since the coefficients of A tilde will be smooth, the asymptotics of eigenvalues for H tilde no, and we will prove that the difference is small in the sense of Birman-Slamiak lemma, namely that the asymptotic coefficients go to 0. Now it's time to see how the approximation goes. So with which matrix we approximate as which smooth coefficient matrix will approximate our bad coefficient. So theorem on approximation. I remind you that our matrix A of x, bad matrix, is bounded, elliptic, and it is continuous at the point 1 as function of the last variable with values in L infinity. So theorem says the following. One can construct a smooth matrix in the following way. That first, it's also bounded. Secondly, it is also elliptic. And finally, that for any x, the LP difference between the matrix A and the approximated matrix A, LP, P will be chosen later on, is smaller than epsilon. So this is the approximation. We do not, and we cannot approximate it in L infinity sense because there is no such approximate by smooth one, but we can do the approximation in this weaker sense. And according to this, we find the approximating operator with known eigenvalue asymptotics. It is the second step in the general schema drawn. So the first one was to represent the Poincare-Steklov problem as a spectral problem for a compact operator. The second step was to construct the approximating operator. This is done using this approximation theorem. And now our aim is to compare, to find out that the spectrum of the initial operator and the nice approximating operator, they are very close in the sense of Birman-Slamiak lemma. So I return here, and so it is written here in the last line. We want to show that the difference between the initial operator, the approximating operator H, is small in the sense of Birman-Slamek lemma. In order to do this, we need to find some expression for this difference. And here is a very interesting theorem. I remind you that T is the solution of the Neumann problem for our operator L. T star is the solution of the Neumann problem for the approximating operator. Well, the formula is the following, that one can find a multiplicative representation of this difference. So it is x star times y. X and y are bounded with compact operators. They act from, you see operator T acts in the domain from L infinity to from L2 to L2 times CD plus 1, and they have the following form. The operator X is this T minus 1 with gradient, so in this direction, and Y is T tilde minus 1 gradient, and this is B. Here it is the matrix B, which is the difference between these two matrices, matrices of bad coefficients and matrices of good coefficients. Well, what is important in this factorization? We somehow separated the trouble. You see here, operator X. Where is the trouble in the operator X? We will be looking for eigenvalue estimates for operator involving X. You see here, the only non-smooth part is here in T. T is the Neumann operator for bad coefficients. Look here at operator Y. Here, the only bad thing is in this matrix B, because here we have the Neumann operator for the smooth coefficients and so on. So here we have this factorization, and after that we can write the factorization for the difference of operators we described our spectrum. This is the formula. It also can be factorized in the, so it is gamma. I remember that gamma is the restriction to the boundary times the weight. So gamma y star, so this is y, it is y star. All operators which we deal here are bounded, so there are no problems about writing this star. And here, gamma x star, this is the operator x, and one must put one more star to this product. So this is the factorization. And the last, and what is remaining is to find eigenvalue estimates separately, singular number estimates separately for the operator gamma y star, which is a hard work, and to the operator gamma x star, which is a simple work. So as for the first, for this operator gamma x star, where the only bad thing is bad coefficients of the operator T. So here one can again use a theorem which was proved by Grigori Rozenblum and myself some couple of years ago about estimates exactly of this kind of operators. And it gives singular number estimates for these operators. Here, for y star, here you see again y star, we do not know how it acts. Gamma is the restriction. For this operator, it requires some work. Look here, the work with y. So here I recall what is this operator y. It is the solution of the Neumann problem for the good operator time, and to this we must apply the gradient, and to this we multiply by a bad function b. Remember what we know about bad function b. We know that it has a small LP norm along the layers with fixed xd plus 1. So we made this approximation. Here again this y, and here we act as we consider the quadratic form related with the operator y. This is one, and we need to find the eigenvalues, to find the estimate for eigenvalues of this operator, singular numbers of this operator. We consider the quadratic form. Here, to understand the things better, we denote by W this gamma t tilde minus 1 star applied to G. G is a function of the boundary, so this is altogether, it maps function, this operator with star maps function of the boundary to functions in the domain. So this quadratic form, which is written here, can be written in this way. And this is the ratio of quadratic forms which we need to estimate. Here a lot of, in fact, the estimates for this part, they take a considerable part of the paper, and I just clear. So the most of the remaining work is with estimating eigenvalues of this ratio of quadratic form. So there are several steps in this, hard steps. The first one, that we may suppose that this matrix B is supported in a small neighborhood of the boundary, because it's a well-known fact that what is happening with coefficients inside the boundary doesn't influence the Steklov eigenvalues. Now we are going to unfold this terrible expression. You see here, it's a composition of quite a lot of operators. So how are we going to unfold? The main work is the following. We have this ratio. When we replace this norm of function g, which stands in the denominator, by something smaller, then we get the eigenvalues which are larger. And we want to have estimates from above. So our work will be in estimating this expression in the denominator, the norm of the function g, at the boundary, by something smaller. So the first step, we are going to find upper estimate for this function w in the terms of function g, because we want to work only with the function w. So the first property is the following, that this function w, although it has a complicated form, it satisfies the equation L tilde w equal 0. So it's a classical solution, because now we have nice function, nice operator. L tilde is operator with smooth coefficients. So this w satisfies the equation. This operator, which we are studying, this operator from gamma double, which maps g to gamma w. Gamma, I remind you, is the restriction to the boundary. It acts on sigma, and it turns out it is a pseudo-differential operator of order -1. It's a rather simple fact, but nevertheless, I was not able to find a reference, so I had to prove it directly. So we have such estimate for this w, that this gamma w, the restriction of this function w, so this is function w to the boundary, is estimated by this g. Now we use the elliptic regularity. So this w is a solution of second order elliptic equation with smooth coefficient. So the elliptic regularity says that this solution belongs to the Sobolev space of order by 1 higher than the boundary values. So this is the elliptic regularity. So we may replace this g in the denominator by the norm of this w in the Sobolev space of order 3/2. But still, this w is a solution of an elliptic equation. Now, so this is the ratio to which we arrive. So we need to find the eigenvalues, to find the estimate for the eigenvalues of the operator, which is defined by this quadratic form, which is in the numerator in the Sobolev space H3 half, but not in the whole Sobolev space, in the subspace of the Sobolev space, which consists of solutions of our elliptic equation. Well, how to do next? So it was a nice result by Tanya Soslina, which it is the weighted estimate. Generally, if we have a solution of elliptic equation, then inside the domain, this solution is infinitely differentiable. But as we approach the boundary of the domain, it becomes worse. And this lemma by Soslina, they give a quantitative description of how worse is the solution of the elliptic equation when we approach the boundary. So it says the following. So let the function omega belong to some Sobolev space and a solution of elliptic equation. It doesn't even say by what order, it doesn't matter. Some elliptic equation with smooth coefficient, and let r of x be the distance from the point x to the boundary. Then there is such estimate. When s plus kappa r integer is an integer, then you see here the integral of the gradient of order s plus kappa of the function w times the weight factor is estimated via this w, the norm of w in the Sobolev space. So you see this s plus k can be taken as big as we like. It shows that the solution is smooth inside, but as we take this kappa larger, it says that we may estimate it only after multiplying by some weight, which decays fast as we approach the boundary. So this is the result. You see, if in fact we have something exactly this, we have s equals 3 half, we have a solution equation, so we apply this estimate by Soslina for particular values with s equals 3 half, k equals 1 half, and then we arrive to the, again, it's estimated by the variation rational if of the following form. So x to the power x d plus 1 times, you see here, the gradient of second order, and here we have what we had previously. Now look at the expression of the denominator. So it is, well, now we can drop the condition that it is a solution. We have already used it, and drop the condition and consider this this ratio. So we are looking for eigenvalue estimates for the operator, which defines by the form in the numerator in the space which defined by with the norm defined by what is the denominator. What is in the denominator is the quadratic form of the fourth order differential operator. You see here it's the differential, it's the gradient of the second order. Therefore, the whole is the quadratic form of the fourth order degenerate, this is degeneracy, elliptic operator. And here it was a very nice thing that I was able to recall again one more ancient result. Solomyak in mid-70s was very productive, and in particular he was working together with his PhD student Ira Vulis, who unfortunately dropped mathematics. And they have written several papers exactly on the eigenvalue estimates for operators of higher order, of degenerate operators of higher order. And one of the results, I found out, it was not that easy, I found out the exact reference. One of the results is the following for degenerate order 4 elliptic equations. So let the function be the matrix function b be continuous as function of this variable at the point xd plus 1 equals 1. Well, here it must be xd plus 1 minus 1. You see, well, let's be 0 at this point, so that it degenerate. Then the eigenvalues of this operator are estimated by means in the terms of the norm of this b. This is the norm of this b, which is continuous at this point. Here, well, here it must be 0. Continuous at this point. In the sense of L infinity, and look what stands here. Here it stands L infinity norm of this norm b, and here it stands LP norm of this difference on the boundary of some p equals to d plus 2. D, it is the dimension. You see, here we have estimates of this quantity, and it is here we can use the fact which we established quite long ago, that we can make this b, this LP norm of b, small as we like. We apply this and we come to an estimate for this operator gamma y star in the terms of the LP norm of this d in the terms of L infinity norm of this b at infinity. This L infinity norm is bounded, and this goes to infinity as we improve the approximation. But unfortunately, this is not the end of the story. I was very happy when I arrived at this place, but a few hours later I found out that I should not be too happy. If we return to the way how this estimate was obtained, there were two places. I look here. We use elliptic regularity. We use elliptic regularity for solutions of the equation L tilde W equals 0. So the solution can be estimated in the terms of its boundary condition. But the constant in the estimate, it depends on the operator. So if the coefficients of operator are still infinitely differentiable, but their derivatives become large, and these derivatives spoils it when the coefficients of derivative become worse when we try to approximate a bad function. So this coefficient, this c, it spoils, it cannot be controlled when we make this approximation. The same thing is in Suslina's result. The Suslina's result, again, this c, this constant c, it depends on the equation. The worse is the equation, still differentiable. The coefficients are still different, but the derivatives are large. This c becomes worse. So, in this estimate, which is written here at this stage, we cannot control c. You see, b goes to 0. We approximate b. We approximate the coefficient by smaller one. But at the same moment, c deteriorates, becomes larger. Therefore, it required quite a lot additional work. We found out that this W, this operator, I want to find the estimate, consider smooth matrix B. We have this terrible expression for this operator W, which we're studying. This is the operator for which we have already obtained, but estimates but bad ones. But this operator is an operator with smooth coefficients. A very complicated operator, but here one can apply to this operator the Boutet-de-Monvel calculus of pseudo-differential boundary value problems. You see here everything is smooth, and it is the combination of operators in the Boutet-de-Monvel calculus, and it turns out that this terrible operator is a pseudo-differential on the boundary of order -1, and the principal symbol of this operator of -1 is majorated by b of x square. It's the principal symbol. So there are quite a lot of lower order symbols, but the principal symbol is this one. It's easy to understand that b it is 2 times b, one time with star, so it's b square. And finally, one more ancient result. To this operator, we apply Biermann-Slamiak asymptotic estimate for singular numbers or pseudo-differential operators. You see, it was a paper which was published in a rather obscure country, the Soviet Union, in a very obscure journal, even for this country. So it was not very easy. The paper consisted of 2 parts. In one part, there was a formulation and explanation. The other part, it were proofs. And even the part with formulation was translated into English and published. The second part with proofs was also translated by, I do not know any people who were able to find it. I know the text in Russian, and so I write here complication with proofs. And it would be, you see, this result, this estimate, it will be written on the next, and in fact, it's the last slide. This estimate is used, have been used quite often because it's very important. So it was used by many people, and it was such complications. So those who do not read Russian needed to believe, to trust. But it changes last year because in some sort inspired by myself, Raphael Ponge from China. So he's not Chinese, he's Canadian, but Raphael Ponge, he found a soft proof of some particular, the most important particular cases of Biermann-Slamiak results. And now these proofs are published. One can refer to Ponge, not forgetting Biermann-Slamiak, but Ponge had found these results about asymptotics, and as a result, we obtain the same estimate which is written here, but with coefficient C not depending on the approximating operator L. This means that, but means approximation, one can make this quantity as small as one wishes, and now the main Biermann-Slamiak theory applies, and this is the result by Biermann-Slamiak, and so as L d half, this LP norm of B it is the difference of matrices of coefficients goes to 0, then it turns that this difference, that the first term, the first term is small, and the second term is of controlled order. So by Kifan inequality for the product, we obtain our result. So this is the Kifan for the problem. So then standard calculations, and this means that this n sub goes to 0 as we make approximation. This concludes the proof. Well, this is not that easy to follow, but those of you who want to follow the details, and there are quite a lot of details which I was unable to report here, there are, so first of all, The paper is published in Journal Spectral Theory number 3, and those of you who do not have access to Journal Spectral Theory, I think it's open access, but one can take the archive version. They are almost identical. Thank you.
Thank you very much for the talk, Richard. We have time for questions now. So if you have questions, please unmute yourself and ask, or just write them in the chat if you prefer.
Grish, may I ask a question? So, to what extent do you think kind of the assumption of being Lipschitz is just maybe the best possible? You know, the operator in principle you can define for any domain with rectifiable boundary just using the quadratic form. But if you have kind of some rather sharp cusps, it need not be even with discrete spectral. So you cannot go that far, but maybe. So what do you think about it?
I do not see who is it, Lenya?
Yeah. This is it.
Well, thank you for the question. There are several points. One point is that this Weyl asymptotics probably can be extended a little bit further. What is needed here? That the boundary has finite area. It has finite area. This is not that strict condition as Lipschitz. There is a theory, you see, Stephen Hoffman, Marius Mitrea, Michael Taylor, they have written quite a lot of papers. Some of them are 300 pages long about boundary value problems in domains with boundary of finite area or something of the sort. And here the problem can be set. If as soon as it is a finite area, I think that the Weyl asymptotics of more or less this form can be proved, but not by these methods, probably more complicated methods. And it is not. So it is possible. I think it is possible. It requires different methods. It is possible as long as the expression in the asymptotic coefficient makes sense. I think it is possible. You may recall that my very early result, the theorem which I proved 50 years ago and whose name I carry, this result shows that quite a lot of asymptotic formulas are correct as long as one can write them. When the boundary is worse. Right now I'm finishing a paper, again a rather long paper, where for the case where boundary conditions, more or less, something even can be in more or less general form, are set on less regular domains. So fractal domain, fractal boundaries, for example, and so on. So in these cases, I can find eigenvalue estimates. Sometimes they are two-sided eigenvalue estimates, and there the order is not Weyl order. It depends on some, say, fractal structure of the boundary. So if the boundary is fractal, then the order of eigenvalue estimates of what can be understood as generalization of Steklov problem depends on the boundary, on the quality of the boundary. So that's what happens.
Yeah, Grish, it was going to be my next question. What is happening for the snowflake, for example?
Well, you see, there are a lot of snowflakes.
Yeah.
A lot of small flakes, counter sets, and so on. Here, I told you that it is possible to give two-sided estimates sometimes of the same order, but it is known that even in one dimension for fractal boundaries, it is one can prove that the asymptotics is not power-like. You see, it is power term by times some oscillating term.
Some oscillating term. That's what we expect. Yeah.
Yes, yes. My approach, my machinery, the machinery I learned for many years, it cannot handle such asymptotics.
Okay, we'll talk separately about that. It's a long story.
Well, I'll be in Edinburgh next month, and then I'll be in Bath in the summer, I think June or July. So it's possible.
I'll get in touch. Thanks.
Anyone else wants to ask something or say something?
Just to clarify something, it's clear that just finite area of the boundary is not sufficient for having a Weyl law, because if you have a cusp at speed faster than something that looks like a dth root, you have continuous spectrum. So in that case, even if you have finite area, you cannot have a Weyl law. But in the dimension 2 case, for slower cusps than square roots, our proof also had a Weyl law there. So I think there's a lot of subtlety happening in the cusp.
Yes, of course, everything here is not easy. If you remember what I was talking about in this proof of mine, one of key points was this geometrical construction where I had where I required the Lipschitz property in order to make this variable change. If the boundary is worse, one should think a lot how to do this kind of construction.
So one of the things I was wondering is do you think one can use the methods you've proved to get Weyl asymptotics for even in a closed manifold, so no boundary, but Laplacians with very, very rough coefficients. So coefficients that are...
Of course, you see, quite a lot of work here is caused by the presence of the boundary. Because if you have rough coefficients, then it's much easier to handle. You see here, you remember I have written here the factorization formula, the formula how can one write the difference between the resolvent of nice operator and the resolvent of bad operator. In the case when we when we do not have boundary, this formula is much easier. Actually, there are these papers by Biermann-Salomyak in 74, I think, or even 72. There are these papers where they consider very, very, very rough coefficients. It's very hard reading, but it's hard to invent some coefficients which are worse than those that Biermann-Salomyak have.
Thank you, Jean. Thank you, Richard. Anyone else? If not, I think we should thank the speaker again. Thank you very much.